Hi, in this video we are going to talk about the so-called n queens problem, so let's get started. The problem itself is about placing n chess queens on an n by n chessboard so that no two queens threaten each other, which means that they will not be able to attack each other. And of course we have to consider that these queens can move diagonal directions too, and of course upward, downward, and from left to right, right to left, and so on. The original problem was designed to 8 queens, and that's why this problem is usually called the 8 queens problem. But of course we are able to solve this problem in general using as many queens as we want. Gauss was one of the famous mathematicians who worked on this problem, and the second famous computer scientist was Dijkstra, who used this problem to illustrate the power of what he called structured programming. So we have an n by n board, and now just for demonstration purposes we have a 4 by 4 chessboard, and of course we try to put 4 queens onto this board. So let's see. First of all, we try the first place, and because it is the first queen, there are no other queens who threaten this position. We consider it to be a good solution, and we try to place the second queen. Of course, we are going to place as many queens as the number of columns. So that's why we start at the first column, and the second, and the third, and so on. This is not a good solution because the first column queen can attack it. It is not a good solution because the queens can attack in a diagonal manner. But it can be a good solution. They are not able to attack each other if they are placed like this. So we go to the third one. It is not a good solution. It is not a good solution. It is not a good solution because the second column queen is able to attack it, and this is not a solution too. So there are no feasible solution. We have to step back to the previous column and increment the position of the queen there, and this is why it is called backtracking. We go back because we come to the conclusion that with this situation we are not able to solve the problem. So we go back to this, and we come to the conclusion that we have to increment the position. It is going to be a good solution because the first column queen are not able to attack it. And we start again with the third column queen. It is not a good solution because the first column queen is able to attack it. But this can be a good solution. Okay, then we start placing the last queen. It is not a good solution because the first one and the second one is able to attack it. This is not a good solution because the third column and the fourth column queen is able to attack it. This is not a good solution too, and this is not a good solution too. So no feasible solution again. What we have to do? So we have to step back, because this is how backtracking works. We come to the conclusion that there is no feasible solution, so we have to come back to the third column and change the position there. So we go here, and we come to the solution that there is no feasible solution again, so the third column queen are not able to get a position. That's right, so we backtrack again. And we backtrack again because this is the last row for the second column queen, and we come to the conclusion that okay, we have to move the first queen. And because we come back to the original problem and there is just a single queen, we consider it to be a good solution. Then we start again with the second column. It is not a good solution because they interfere with each other. They interfere with each other like this and this. Okay. Then it can be a good solution because no, the column 1 and the column 2 queens are not able to interfere with the third column queen. And for the last one, it is not a good solution. It is not a good solution too. But here it is a good solution. So we are able to solve our problem with the help of backtracking. And how does it work? We assume we go step-by-step basis, and if we come to a situation when there's no feasible solution, we keep backtracking and backtracking again until we come to a situation that's going to solve our problem. I mentioned in the previous video that we can construct a search tree, and we are able to make a depth-first search on this search tree in order to get the good solution for our n-queen problem or any backtracking problem. And how are we able to construct a search tree? We start, for example, not by a 4x4 or an 8x8 table, but we start with a 3x3 chessboard. And this is the starting situation when there are no queens at all. We try to place the first queen, and we can make it 3 different ways. We place it to the first row, the second row, and the third row. And we don't know that what's going to be a feasible solution. So we take all of them and we keep constructing a tree-like structure like this. For example, if we place the queen to the first column and first row, we are able to place the second column queen 3 different ways, to the first row, second row, and third row. Of course, we may come to the conclusion that these are not going to be feasible solutions, so we can prune these subtrees. And why is it good? Because if we have a single node can have a huge subtree, because for example each of the node can have several possible solutions and outcomes. And I'm not sure whether you are familiar with chess engines or how to solve the tic-tac-toe with the help of these tree-like structures, but it is quite common to construct a huge tree, and with the help of heuristics we are able to prune this tree. And why is it good? Because we are going to get rid of so many nodes in our tree that it will be easy to traverse it with the help of a depth-first search, for example. So when pruning, we get rid of the whole subtree. For example, we come to the conclusion that the first two, these solutions are not going to be feasible because the 2 queens are able to interfere and attack each other. So we are going to prune the whole subtree, and we are going to get rid of 1, 2, 3, 4, 5, 6, 7, 8 nodes at the same time. And after getting rid of these nodes, the leftover of the tree may be so small that we are able to get an exact solution with the help of a graph traversal algorithm, such as, for example, depth-first search. So this is why it is very, very important sometimes to construct a search tree. And that's all about backtracking. Thanks for watching.